In this video I'm going to illustrate how to carry out a binary logistic regression using SPSS. Binary logistic regression is utilized when you have a categorical dependent variable that has only two levels. Those levels are often coded 0 and 1. 0 referring to a baseline category or a baseline group, and the 1 referring to a target group. So essentially there are other types of logistic regression as well. There's ordinal and multinomial logistic regression. Ordinal logistic regression is utilized when you have three or more categories on the dependent variable, and those categories are ordered. And multinomial logistic regression is utilized when you have more than three categories and those categories are not ordered. So for this particular example, like I said, we're going to run a binary logistic regression. And so let's consider this scenario. We're studying predictors of the likelihood that individuals seeking services at an on-campus counseling clinic will terminate treatment within 2 months after beginning services. So terminate is our dependent variable. We've coded at 0, meaning no termination, and 1, meaning that the person does terminate within the 2 months. Our predictors for the model include sex, which is coded 0 for male and 1 for female. Year in school, coded 1 for freshman, 2 for sophomore, 3 for junior, and 4 for senior. And then symptom severity and avoidance of disclosure. So these are going to be continuous measures with higher scores on them reflecting greater symptom severity and avoidance of personal disclosure, respectively. So here's our data in SPSS, and we have data on 45 hypothetical individuals. So we have our variables. Each column is representing a different variable. You can see for case 7 or person 7, that person was someone who did not terminate within 2 months. This is that person's scores on the two continuous measures. That person was a male, and also that person was a freshman. Person 28 did terminate within the 2 months. This is that person's scores on the two measures. That person was also a male, and that person was a junior. So let's run our logistic regression. And for this example, for the first example, we're going to use avoidance of disclosure, symptom severity, and sex as predictors of the likelihood of terminating within the first 2 months. So let's go to Analyze, Regression, and Binary Logistic. And we'll move Terminate, which is our dependent variable, to the dependent box. Avoidance of disclosure and symptom severity, which are both scale variables, as predictors. Sex is a nominal variable, but because sex only has 2 levels, we can go ahead and enter that because it's by default it's a dummy variable, so there's no need to specify sex using the categorical function that is used with categorical data with more than 2 levels. If we included year, which we're not going to do in this particular illustration, then we would be utilizing the categorical function in order to have SPSS generate dummy variables to capture the information contained in the year variable. So in terms of various options, we will click on Save. We can ask for predicted probabilities and predicted group membership. The predicted probabilities that would be saved to our data set is the probability that a given case falls into the target group, or basically the group that is coded 1. So for our data, it would be the probability or likelihood that a case falls into the group coded 1, which is the group who terminated within the first 2 months. Based on those predicted probabilities, the program will generate predicted group membership. And so predicted probabilities that are equal to or greater than 0.5 are those cases are assigned to the group that's coded 1. So they were predicted to be in group 1. If a case has a predicted probability that is less than 0.5, then that case is predicted to fall into group 0, or the non-termination group. So when we click under options, we can ask for various things. We're going to ask for the Hosmer-Lima-Show goodness of fit test and the confidence interval for the odds ratio. You'll also notice down here you have a classification cutoff, and the default is 0.5. This classification cutoff is what is actually utilized in order to take the information from the predicted probabilities to generate predicted group membership. So essentially, it's a threshold for deciding whether a case is predicted to fall into group 1 or group 0. So you can change this if you like. Like I said, the default in SPSS is 0.5. So when we click on OK, we get our output. And in fact, before we do that, let me just kind of show you what I was talking about with the predicted probabilities and group membership. So we have a variable now for predicted probabilities. So all these predicted probabilities right here are less than 0.5. And so because of that, the program, using that threshold of 0.5 to assign probability values, these individuals were all predicted to fall into group 0, which is the non-termination group. This person right here and this person right here, the probability values for the likelihood of falling into group 1 is greater than 0.5, and so these individuals were predicted to fall into group 1. So these are predicted group memberships based on the model, and over here on the terminate variable, these are the actual group memberships. So you can just kind of see right here that you have a person who is predicted to fall into group 1, and actually they fell into group 0, and so that's actually a miss in terms of the model, in terms of accuracy. And same goes for this case right here. But you also see that we have a number of individuals who were correctly classified. They were correctly predicted based on the model to fall into the group 0. By the same token, if you look at the group coded 1, you can see that this person, this person, this person, all three of these individuals were correctly classified. You can see that this person right here was incorrectly classified based on the model. So, but in large part, it looks like just kind of eyeballing the predicted values and the predicted group memberships. It looks like that we have decent prediction taking place, but it's usually better to kind of discuss that using more summary measures. So looking at our output, you can see that you have what are beginning block and block 1, and essentially the beginning block is an intercept only model. Essentially what happens in this case is the only predictor, if you will, is the intercept, which is actually a constant. So really this is a null model, and it doesn't really tell you a whole lot except what the predicted accuracy and classification would be in a no predictor model, and that happens to be about 55.6%. You'll notice that for our terminate variable, we had 25 individuals who were observed to be in the terminate group, and based on the intercept only model, all 25 were predicted not to all 25 were actually predicted to terminate. So we had an accuracy rate of 100%. We had 20 individuals who were observed to terminate within the first 2 months, and you can see that all 20 of those were predicted based on the intercept only model not to terminate. So in other words, these were all misses right here. So in terms of classification accuracy, it was 0%. So the overall accuracy rate is 55.6%, and you can see that just pretty much mirrors what we would have if we asked for like a bar chart. And you can see right here that we had 55%, 0.6% that fell into the group coded 0, 44.4% that actually fell into the group coded 1. So you can see that the overall classification accuracy mirrors those percentages that we saw just a second ago. So what's most important, or what's really important, is looking at the predictor model in terms of goodness of fit, and we can look at it in an omnibus sense, so overall model fit, and then we can also go back and look at the individual predictors to see which ones are contributing to the global fit. So there are various ways in which we can assess the overall fit of the model. We can compare the fit of our model, the predictor model, against the fit of a null model or intercept-only model, and that's what this chi-square model test is right here. So if this chi-square value is statistically significant, we would interpret this to mean that our prediction model fits significantly better to the data than a null model with no predictors. So from that standpoint, we're comparing our predictor model against a null model, and if this is significant, then we have a significant improvement in fit. Then we have some descriptive fit statistics. We have the -2 log likelihood, Cox and Snell R-square, and Nagel-Kirke R-square. The -2 log likelihood, generally speaking, what you're looking for are lower values. And just kind of eyeballing this by itself, it doesn't really tell you a whole lot in terms of in any kind of absolute sense how good a fit we actually have. This is actually probably more useful from a comparative standpoint if we're comparing different models. But the Cox and Snell and the Nagel-Kirke R-square values are what are referred to as pseudo R-squares. So, and what they're designed to do is to represent sort of an analogy to the R-square value that we have in least squares regression. So, if you look at these values right here, we might say, well, and if you multiply them by 100%, we might say, well, our model, our predictors are explaining roughly 47 to 62.9% of the variation. The thing to note is that the Cox and Snell doesn't have an upper limit of 1 like you have with the R-square value. So the Nagel-Kirke R-square actually does range between 0 and 1. So you want to keep that in mind. And also, again, these R-square values are pseudo R-squares, so it's to kind of give us an analogy to the R-square that we have in traditional least squares regression. Now, another option, which Tabachnik and Fidel talk about in their textbook, which I actually like a lot, is essentially to compute a phi coefficient and square it. And basically a phi coefficient is just a correlation coefficient, or the correlation between two dichotomous variables. So if you square that value, then you end up with an R-square value, and then you can talk about the proportion of overlap or shared variation between variables. So the two dichotomous variables that I'm referring to are, if we go back, are the predicted group membership and the actual group memberships. So both of these variables are dichotomous, so we can actually compute the phi coefficient just by going to correlate, bivariate, and the phi coefficient is we can compute it using the Pearson option in SPSS. So essentially the phi coefficient would be the Pearsons are between two dichotomous variables. So we click on the terminate variable that we have right here, and move our predicted group membership over as well, and we click on OK. And you see that the correlation between predicted and actual group membership was 0.687. So essentially, we can just really quickly calculate R-square if we just take 0.687, square it, which gets us 0.472 or thereabouts. So we, multiplying that by 100%, we would say that that our predicted group membership explained about 47.2% of the variation in actual group membership. So that's a pretty good proportion of variance accounted for. So like I said, this is a really handy way that we could compute R-square that's probably more akin to what we would think about when we're running least squares regression. Nevertheless, you have to kind of go through that extra step of generating the predicted group membership and then correlating predicted and actual group memberships. So moving on, we also have the Hosmer-Lebesgue test, and this goodness of fit test, this is still using a chi-square test, but in this case, the chi-square, what we are looking for is a non-significant value. In this case, we find that our p-value is equal to 0.614. It's non-significant, which is actually a good thing. It's consistent with our data, our model fitting the data. Just kind of keep in mind that the Hosmer-Lebesgue test is not a highly recommended test of model fit. There are various problems with the test. Nevertheless, it can still be useful as a screener for looking at overall fit. Scrolling down, we see that we have the classification table, and this is yet another way in which we can look at overall fit in terms of classification accuracy. Earlier, I was discussing how we, just kind of looking at or eyeballing the predicted group memberships and the actual group memberships, we saw, that these individuals were all correctly classified based on the model. This individual was not correctly classified. This one was not correctly classified. This one would not be correctly classified as well. But the classification table summarizes the hits and misses in terms of classification accuracy. So for starters, if we go to the look at under observed right here, this is our variable, and we have those individuals who did not terminate within 2 months and those individuals who did. So altogether, we had 25 cases. If we just take this value and add it together, that's 25 cases that were that actually were observed not to terminate within the first 2 months. And we had, if we add these two values, we have 20 cases that did. So kind of, going back to that null model that I was showing you, we had 25 and 20 respectively for those two categories. Now, the cells are capturing the number of cases that were predicted to fall into a category in relation to the number that were actually in that category. So we had 23 individuals who were both predicted to not terminate and who actually did not terminate. So that actually represents an accuracy in classification of 92%. In other words, if we take 23 of those individuals who were predicted and divide by the 25 that were actually did not terminate, that gives us a classification accuracy of 92%. So that's really quite nice. Obviously, the 2 right here is representing misses in terms of classification accuracy. So essentially that last 2 right here, we have essentially 8% that were incorrectly classified based on the model. At least incorrectly classified because these individuals were predicted by the model to terminate, and yet those individuals were actually were folks who did not terminate. So these are misses, and actually another way of referring to this are false positives. So now we have, in terms of those individuals who were classified, who actually were who did terminate within 2 months, we had 15 individuals who were correctly classified by the model. So we had individuals who were predicted to be in Group 1 that actually were in Group 1 is 15. So if we take the 15 and divide by all the individuals that were that did terminate early, we have a classification accuracy rate of 75%. So that's still pretty good in terms of correct classification. So The remaining 5 are misses, and these would be basically false negatives. So individuals who were predicted not to terminate, but who actually did terminate. So we had an accuracy rate of 75%. So this last 5 individuals right here represented the remaining 25% of the cases. So if we take our 23 and 15 and essentially add those together, which would get us 38, and we have an overall size. So we had 38 that were correctly classified. Divide by, remember we had 25 in group 1 and 20 in group 2, so essentially that would be 45. Then that gets us an overall classification accuracy rate of 84.4%. So really the remaining 15.6% are these guys right here that were misclassified. So what does this really tell us? I mean, when we're looking at just the global fit of the model, it appears that our model represents a significant improvement in fit over a null model. When we look at the R-square values, the pseudo R-squares and our actual R-squares, which was, I think, actual R-square was 0.471. We're doing pretty good in terms of explaining variation in the dependent variable. The Hosmer-Loomis show test was non-significant, which is also an indicator of good fit. And then we see, based on our classification table, we have an overall accuracy rate of 84.4% in terms of predicting who was going to fall into the group that terminated within 2 months, which is the group coded 1, and those who didn't. Just kind of keep in mind, too, that it appears that the model actually does a better job of predicting who will not terminate as opposed to those who will terminate. So, because the accuracy rate is actually higher in terms of predicting who won't terminate as opposed to those who do. But again, the overall classification rate is 84%, and we still have a pretty decent classification rate when it comes to predicting who will terminate. So looking beyond just the global fit of the model, we can also look at the individual predictors and determine which seem to be doing most of the work in terms of helping us with our classification accuracy and our overall model fit. So these are the regression coefficients, and basically they're interpreted as a change in log odds or logits for every 1 unit change or increase on predictor variables. And so, we can actually convert logits into probabilities, meaning that, essentially you could, even though we're referring more specifically in terms of change in log odds or logits as a function of change on the predictors, basically a positive value is meaning that as scores increase on the predictor, the probability of falling into the target group coded 1 is increasing. If you look and you find a negative coefficient, that's essentially telling us that as scores are increasing on the predictor, that we're having decreasing likelihood of a case falling into the target group. So, and we have significance tests, basically wall chi-square tests or significance tests for each of these effects. So looking at the avoidance of disclosure measure, we would interpret the regression coefficient to mean for every 1 raw score unit increase on avoidance of disclosure, we have an increased likelihood that the person terminates within the first 2 months. And more specifically, the log odds of falling into the terminate group is increasing by 0.354. And we see that predictor is statistically significant. For the second predictor, symptom severity, we can interpret this to mean that for every 1 unit increase on symptom severity, there's a decrease of 0.34 in the log odds or logits regarding falling into the target group. More generally speaking, it just basically means that for every, as scores are increasing on symptom severity, the likelihood or the probability of falling into the target group is actually decreasing. And we actually find that that predictor is statistically significant. When we look at sex, remember that males were coded 0, females were coded 1. So a negative value right here means that essentially, if you were male, then the likelihood of which again they were coded 0, the likelihood of falling into group 1, which is the terminate group, is actually increasing. If you're female, which again females were coded 1, the likelihood of falling into the terminate group is actually decreasing. But we see that effect was not statistically significant. So really the global fit seems largely to be a reflection of the avoidance of disclosure and the symptom severity predictors. Now in this column right here, the EXPB column, these are basically referred to as odds ratios. And it reflects the amount of change in odds as a function of change on the predictor variables. And odds basically are calculated as a ratio of probabilities. So we can say that the odds that a person has a score, a dependent variable score equal to 1, meaning that they terminate, is essentially a ratio of the probability that y is equal to 1 divided by the probability, 1 minus the probability that y is equal to 1. So this is an odds, and essentially, so each case will have an odd, just like they will have a logit score, they will also have an odds value, and then they will also have the predicted likelihood of actually falling into group 1. So the odds ratio that you have right here, this is, like I said, this is called an odds ratio, and basically this refers to the amount of change in the odds for every 1 unit change in the on the predictor variables. But keep in mind the odds, the change is multiplicative as opposed to additive. So it's not like it's not interpreted in exactly the same way as a least squares regression. So we would say, for instance, that for every 1 unit increase on avoidance of disclosure, the odds increase by a factor of 1.42. So in other words, the odds are changing by a multiplicative factor. So for symptom severity, we could say then that for every 1 unit increase on this variable, the odds are changing by a factor of 0.711. So what this basically means is that when you have an odds ratio value of that's greater than 1, what that means is that the odds are actually increasing. So the odds are increasing for every unit change on the predictor variable. If the odds value is less than 1, that means that the odds are actually decreasing for every 1 unit increase on the predictor variable. So it's decreasing by a factor of, I'll just say multiplied by a factor of 0.711. Here, the odds are being multiplied by a factor of 1.425. You can see, so basically if this value right here, if the odds ratio is equal to 1, that means that there is no change in the odds as scores increase on the predictor variable. So in other words, and basically if the odds ratio is 1, what you'll have is a regression coefficient that would actually be equal to 0. So just kind of keep in mind that an odds ratio that is greater than 1 means that the odds are actually increasing by a factor of that number right here. And that also means that the regression coefficient is actually going to be positive. If the odds ratio is less than 1, then what that means is that the odds are decreasing, and what you'll see in that case is a regression coefficient that is actually a negative value. And if the odds are actually equal to 0, you would have a regression coefficient that's actually equal to 0. I mean, excuse me, an odds ratio that's equal to 1. That would mean that you would have a regression coefficient with an odds that is actually equal to 0. The other thing to kind of note too, we also requested a 95% confidence interval for the odds ratio. So essentially, you can interpret it this way: if the odds ratio that essentially it's like this. If you find that a value of 1, which is actually just the null, so an odds ratio equal to 1, which is the null, if the null falls between the upper and lower limits of the confidence interval, then you cannot reject the null, and basically you would be saying essentially that the predictor is not having a significant impact on the odds of target group membership. If 1 falls outside of the upper and lower bound of the interval, then you would interpret that predictor to be significant as well. So in this case, you can see that 1 does not fall between the lower and upper bound here, so you can see that we have a significant change in odds for every unit increase on avoidance of disclosure. Here you can see that we have that 1 does not fall within this interval right here. So you can see we have a significant decrease in the odds as scores increase on the predictor variable. But here we see that 1 does fall within this interval, and so that would mean that the predictor is not a significant contributor in the model.